Alright, welcome back to Physics with Miyoshi. We are going to talk a little bit more about work today. First remember, problem solving. Make sure you draw a picture. Pictures are always great. Determine what energy is changing and what work is being done. Remember that work and energy are interchangeable. Oftentimes we'll say work when we mean energy, and oftentimes we'll say energy when we mean work. But they're interchangeable, so don't worry about that. Make sure you set up your equations, equation or equations, and then solve your system of equations. Now, most of the time for energy stuff, you're going to start off with an equation that looks something like this. Energy initial is energy final. And every once in a while you'll have something like plus losses. Okay, and sometimes over here you'll have plus work that you're adding in. Okay? But remember that energy initial is energy final. That's our main equation. And then if we put more energy in, or we lose energy, that's kind of an addition to that. Okay? Alright, so let's look at this. Oops, not that one, this one here. Here's a couple, we're going to go through a couple problems. But before that, I want to talk to you about negative work. Okay? If you look, well, we'll just think about negative work first. How many folks have ever lifted weights? Anybody ever lifted weights? Anybody ever done bench press specifically? Okay, has anybody ever done negatives bench pressing? What's a negative? Okay, you lift the weight up, or you have your spotters lift the weight up, and then you go down as slowly as you can till you touch your chest, and then if you're doing the bench, and then you have your spotters grab it again, they pull it up, and then you come down as slowly as you can. So why do they call those negatives? Anybody have an idea? Well, the reason why they call them negatives is because in essence, if your hands are sitting right here and you're pushing up, the force is going up, but the displacement is actually negative. So if I look at the displacement here, the S, if you will, and the force, if you will, they're going in opposite directions. And because they're going in opposite directions, that's why the work is actually negative. Okay? So in a negative, when you're doing bench press or other weightlifting, and I would suggest, from my perspective, from a safety perspective, that really negatives are really only useful for bench press. They're not very safe on squats and other things. But the displacement is negative from the force. That's when you have negative work. And if we look at the equation, work is force times the displacement times cosine theta, right? If we think about this, what's the theta between my force and my displacement in this case? Well, the angle there is 180 degrees, and so the cosine of 180 degrees is -1. Okay? So that concept of negative work is very important, and that's when we come to this problem right here. Okay? It says a mass attached to a 3 meter, a mass M, so that's this upper one, is attached to a 3 meter mass by a rigid bar. Now we could talk about torques and all that kind of stuff, but we weren't going to worry about that for right now. This does fit in this equation. The bar is negligible, and it's got a length of L. Okay, initially the smaller mass is located directly above it, and then it's going to go directly below it. So what work is necessary to turn this rod 180? So if I look at this guy here, all I want to do is turn this guy 180 degrees. Okay? So how much work is going to be done to do that? Well, in reality, you'll have enough information to figure that out. From what we've talked about before, and with this little explanation about negative work, we should be able to determine from these answers which one it is. Okay? Do we have an idea what we might use? What kind of energy we're talking about here? Anybody? Well, the kind of energy we're talking about here is really gravitational potential energy. So I'll just call it PE and label it G. And if you recall, gravitational potential energy is mgh. Okay? So now, and actually let's look at it that way. This is mgh, so in this case I'll change the h to an L. And then if I wanted this guy to go, if I consider this to be 0, it would be 0. But now all I want to do is swap these two guys. So how do I do that? Well, let's look at it here. all we really need to know is gravitational potential energy, because, and remembering that it doesn't matter how I get to that final position, right? Gravitational potential energy, gravitational energy is, the force of gravity rather, is a conservative force. So it doesn't matter what path I take, right? So it doesn't matter if this guy turns, or if it's flipped directly, or if this is not rigid and we have to move it somehow. It doesn't matter how it gets there, as long as this is above there and this is below there, that's the final position, and that's all we need to worry about. So how much work is it going to take to get this guy from there to there? Well, that's just changing my potential energy. So that's going to be 3m g times L in this case, right? Okay? That's great. That's probably one of my that's not one of my answers though. And the reason why it's not is because this guy's going to come down, and since it's going down, its potential energy has changed, and it's actually negative mgl. So the total potential energy then is going to be the difference between those, or adding those guys up. So in reality, this guy ends up being 2mgl, which is this guy right there. Okay? Now, the reason why they throw this number there, the 2 pi in there, the reason why, the 4 pi, the reason why they do that is because somewhere in here, you're going to learn about torque. And so if you try to figure this out by using torque, you might come up with something like this. I didn't try to figure this out yet, doing torque, but you should come up, even if you did use torque, you should come up with the same kind of thing. Okay? Yes?
So, what happens with 3 to get from negative to negative 2?
Oh! Okay, what we did was, this potential energy has to do with just the mass, the m, and it's going to go negative. It's going to basically be negative, because it's going from up here to down here. And this guy here was for the 3m. So the question was, what happened? How did this guy get to be from 3m to now be 2mgl? Well, the reason why is because it didn't. The work to get this guy up there was 3mgl, and the work to get this guy from there to there is actually negative mgl. So when you add those two guys together, you get the total to be there. Okay? We're not going to use torque. Okay? So we actually have positive work to get the 3m up and negative work to get the m down. And that's why I need to talk about the negative work too. Okay? Alright. Is that okay? Okay.
Did you talk about potential energy and stuff on Friday when I was here?
We did.
Okay, so I'll watch it.
Okay. And we'll look at that too. I can help you with that too. Here we go. We have this one here is really a trigonometry problem. Actually, it's a Pythagorean theorem problem. Okay? And hopefully you guys will recognize that here as we read the problem. A body of mass 5 kilograms at rest is acted on by 2 forces, 3 newtons and 4 newtons, which are at right angles to each other. So it doesn't matter which direction we call them, but they're acting something like this. Okay? And if you call, well, then we'll talk about it in a minute. The kinetic energy of the body at the end of 10 seconds, so we know our time is 10 seconds, is what? So we're going to look at these guys here. So the problem here is actually a kinematics, and it's a force problem, and it's also an energy problem. So you have to kind of do all those. But in the beginning, all we have to realize is that this guy, whoops, let's separate that out. Well, actually, it's just to do this. What we really want is we want to draw a triangle. And remember, when we draw a force vector, we want to add the vectors together. We're going to add them head to tail, right? Yes?
When it says 10s, does that mean 10 seconds?
Seconds, yes. 10 seconds. Okay? So we know that this guy is 4 newtons. And this guy is 3 newtons. So Pythagorean theorem says that this total force has to be what? 5 newtons. Okay? So a 3, 4, 5 triangle. Hopefully you all recognize that. So my 3, 4, 5 triangle, it doesn't matter which direction it's going. All we know that it's going to act for 5 seconds. Or for 10 seconds. Okay? So, let's see here. Let me look at my notes here real quickly. So, we know that our force is our mass times acceleration. Okay? It doesn't matter what my mass is. I can always throw in a mass. Oh yeah, it does. It says 5 kilograms. So I have 5 kilograms and 3 and 4 newtons. So I have 5 kilograms, and I know my force is 5 newtons. So what's my acceleration? Well, acceleration is just going to be 1 meter per second squared, because that's 5 newtons divided by 5 kilograms is 1 meter per second squared. Okay? So once I know my acceleration, what's going to be my final velocity? Well, I know it starts from rest. So I know my V initial is 0 meters per second. I want to find my V final. Why do I need to find my V final? Because I know that kinetic energy is 1/2 mv squared. Okay? So hopefully you are remembering this. You're going to need this equation lots. So we want to find that V final. So how do we find the V final knowing the V initial and the acceleration? Well, I would always go back to this equation here. A is delta V over delta T, which is V final minus V initial over my time. And so I know my acceleration, I know my V initial is 0. So now I can just rearrange the equation. So my V final is acceleration times T. I know that's 1. I know that's 10 seconds, so my V final must be 10 meters per second. I just plug that in this equation, and I have 1/2 5 kilograms, and I have, what was it again? 10 meters per second. Square that. That's 100 times 5 divided by 2. That's going to be, what, 250? So it looks like it's that. Now, on the AP exam, you're not going to have that much time, but this is one you might want to look at that. Yes?
So why can't, so I got a different answer the way that I did it, but why can't you do work is force times distance and know that your total force is going to be 5 meters and then your distance is going to be 10 meters because your acceleration is 1 meter per second. And
That would work if this was velocity, but this isn't velocity.
Oh, okay.
This is acceleration.
Okay.
Okay? Did everybody get that question? The question was, why wouldn't... She got a different answer because she looked at this acceleration as velocity instead. And that's a common thing to do. Remember, acceleration is change in velocity, not velocity. Okay? In this case, the V is speed, not velocity, because remember that energy does not have a direction. It's only got a magnitude. So it's what? If it doesn't have direction, but it has a magnitude, it's a... Somebody said it, I think, scalar? Okay, it's a scalar. Okay? One last one real quickly. Alright, this one here is a ball bearing. We got a little ball, and we're going to throw it down. It's going to hit the ground and bounce back up. But when it comes back up, it's going to reach a level that's higher than when it started. Okay? So we have a steel ball bearing thrown vertically down, bounces from the floor 5 meters higher than original level. With what speed was the ball bearing thrown? Okay? So the main thing here is this guy here. Oh, and it says, assume the elastic collision on the floor and gravity is 10 meters per second squared. Okay? So the big part here is that this guy is 5 meters. Alright? Now remember what I said about the original equation we want to look at. Really, it's energy initial is energy final. Okay, especially in this case, elastic collision, that means that there's no losses. Okay? In this case, what's my initial energy? Our initial energy, what kind of energy is it? Anybody see?
Potential.
It's not potential in this case. Well, there is some potential, and there is some kinetic, because we know it's moving downward. So I'm going to ignore the fact that this is, well, we don't know how far it is off the ground, right? This distance here is not given. We have no clue what it is. But it turns out it doesn't matter. Okay? Turns out that that doesn't matter. So if we really want to do this correctly, we would say our potential energy, gravitational, okay, plus our kinetic energy, initial, equals our potential energy, final, plus our kinetic energy, final. Okay, now up here, it's the highest it goes. So at the top of what's the velocity at the top? What's the speed at the top? 0. So that's my V final is 0. So that means my kinetic energy must be 0. The beautiful thing about this equation right here is that a lot of stuff is going to go away when you figure it all out. If I think about the potential energy, really, I want to know the change of potential energy. So that's really the potential energy from there, the difference of potential energy between there and there. So I can really call this the change of potential energy. Oops, we'll do that the other way. My change of potential energy equals my kinetic energy initial. Okay, now the reason I can do that is because if I call this x, that height, then the potential energy initial is just mg times x. Okay? And at the end, the height here difference is potential energy final is mg x plus 5. Okay? So my change of potential energy then must be the difference between the two.
5.
What's that?
5.
Which is, in this case, m times g times my 5 meters. Okay, so that's why I can do that. So let's play around with this a little bit. Oops. So my kinetic energy, if you recall, that's 1/2 mv squared. That's going to be equal to m times g times h. In this case, my h is 5. I can get rid of the masses because they divide out. Yes?
How did you get from the PEI plus KEI step to the KEI step right below it?
This one here?
Yeah.
It's because you're
Oops.
subtracting PEI from KEI so that PEIs are both on the same side. So that's what's changed.
This question here, from here to the last one I just did.
Oh, okay.
The reason why is because I just changed this to a change of potential energy. And the change of potential energy is just this guy here. It doesn't matter how high it was. Okay, does that make sense? Okay, so let's see, let's do this again. 1/2 mv squared is change of potential energy, which in this case is just mgh. Turns out that the masses don't matter. We divide those guys out. V squared, so we can just rearrange this guy to be v squared is 2 times g times h. And you've probably seen that equation before back from kinematic stuff. And so we can now say, let's just go down a little bit farther. We can then say that v is the square root of 2 times g times h. If we assume, like it says, it's 10 meters per second squared, then this guy then becomes square root of 2 times 10 meters per second squared times the height, which is 5. 5 times 2 is 10. 10 times 10 is 100, so this becomes square root of 100. The units are meters squared per second squared. And this then becomes 10 meters per second. Okay? Which is this guy right here.
Why does that have a minus 1?
The -1 means the second is to the -1. So this is like meters times second to the -1. So this is the same as
Oh,
meters
meters
per second
Okay.
squared. Oops, second, sorry, no squared.
Just they didn't have superscript on it.
Yeah, there's no superscript. Yeah, I think it might be the translation from Word and that kind of stuff. There's no superscript on this one. It's just, these guys are all s to the -1s.
Gotcha.
Okay, sorry about that. And I don't know if it turned out that way on your worksheet too, but that's, sorry about that. Okay? Is that okay? We okay with that one? The nice thing about this one is it changes, it looks at your potential energy and kinetic energy, and you can see that the nice correlation there. And the other nice thing about this is, if you look here, we end up with the same equation as we would have if we had done this with kinematics. It's the same exact equation, but we came at it from a different way. Okay, so anyway, that's just a few problems on how to do energy, potential energy, kinetic energy. And so come on back next time. We'll see you here for more physics with Miyoshi.